Okay, the homework I said was due yesterday. Anybody have any issues with this?
I had the issue with the first one for F. It was asking to find alpha for the field controller, which confused me. I wasn't sure how to go about finding.
If you go through my notes, it should be clear. The field control is alpha F. So we've gone through this in class also. So we go up to the picture of the drive. You've got your field right here. That's your field, right? This is your armature. And here the control variable is alpha F. So what you're supposed to do is find alpha F for that case. Um, Remember that the general expression for any alpha, and then I'm going to ask if, I think it's Mike you were asking the question. Was that Mike asking the question?
Yeah.
So I want to make sure that that it's clear, okay? Remember we have this general expression. We know that the drive voltage, averaged drive voltage, that's what we're applying to the armature. Or we have the average drive voltage for the field, that's being applied to the field, V sub F. So in the first case, we had that average voltage is going to be 3 over pi. That's because it's averaged over one 60-degree cycle, root 2 V line to line of the source. Okay, that's right here. Times cosine of alpha drive. V field is 3 over pi root 2 V line to line of the field. So that was, we create a field line to line voltage here. V line to line of the field. That's cosine alpha F. So, for example, we'll talk about the field. The circuit looks like this. You've got a field inductance and a field resistance. But in the steady state, so there's the voltage V sub F is being applied to that. In the steady state, there's no voltage drop across the L sub F. So you used to have V sub F over across R sub F. And that gives you I sub F. What we have is we've got lambda AF, right? So lambda AF is essentially the mutual inductance between the armature and the field winding, times I sub F. We really don't care about what this is. We just know that it's proportional to I sub F. So if you change, if I sub F changes, the lambda AF changes. And we know that the voltage back EMF, E sub A is lambda AF times the speed. So we had to weaken, I believe it was where we were going to a higher speed, or were we reversing the speed in that question, Mike?
Speed was doubling.
Yeah, you're doubling. Okay, so if the speed doubles, you're limited in how much voltage you can apply to the motor by uh, the by this V line to line source. That's limiting you. And so what you've got to do is you've got to reduce EA to operate at higher speed. So then how do we do that is by reducing I sub F. I sub F is equal to V sub F divided by R sub F. So we know this. That was given. Now in the homework problem, I'll go back to the class problem, right? Because I don't have that right off the top of my head. But I did give you a field resistance, right, in the homework?
Yes.
Okay, so you have a field resistance. I gave you a line-to-line input voltage, a line-to-line voltage for the field. Did I do that?
Yes, you did.
Okay, so you've got, it was 208. Okay, so what you've got is you've got V sub F is going to be 3 over pi times root 2 V line times, well, symbolically it's V line to line field times cosine alpha F. And this is what you were supposed to get, right? Is that correct? Okay, and then divided by R sub F. Okay, so we know R sub F. And so I guess we don't have to, let me just do this symbolically then. So the question is, if we know, what we really have to do is we can see right here that you can change the field current by changing alpha F. If alpha F increases, then I sub F reduces, it goes down. Because if you had alpha F equals 0, then that would be the highest field current. We gave you a nominal. Well, you don't even have to have a nominal lambda. Okay, so we gave you, in the problem, did we give you the nominal field current? Did you have that in the problem? Maybe I should just look at the problem so that I'm looking at this, not having to ask. But tell me that in the meantime.
I no.
Let's take a look.
I don't think the field current is given.
Okay, well, let's take. Okay, did other people have the same challenge here with this? Because I could have missed something, but let me look. I'm opening this on my other computer so you're not seeing what I'm looking at, so I can keep this screen up and I'll write down. But okay, so in problem number 2, I gave you lambda AF, okay? And, okay, I think that's the problem. I didn't give you, did I give you RF?
Yeah, you did give RF, and it was for the first problem. It was 1.5 over
Oh yeah, but not for the second problem. You're trying to solve problem 1 or problem 2?
Problem 1F, the last one.
Okay, I got it now. Okay, that's fine. Okay, let's go through it. Let's this still applies. Okay, we're looking at homework problem number 1F. Okay, so basically, again, and we went over this in class a few times briefly, but then I put up those notes to help you. So in this case, you've got a PWM controlled drive to the armature, and we've got a phase controlled or thyristor, right, of the field. Okay, so what I gave you was, let's just consider the nominal operation. The alpha F, that's 30 degrees. See, that was for the 208 volt RMS supply. That's the line-to-line voltage supplying the field. Don't have a figure, but it's the same thing that we've been talking about. And then I think I made the figure of the drive in that note I put up. Was that clear? Do I need to make a figure here to show you?
No, I think that's clear to me.
Okay. Okay, so we have this. So then what we can do, we can find the nominal field current and the nominal voltage. So that's probably what you might want to start with. You're going to say, I've got the field, nominal rated field is going to be equal to 3 over pi root 2 times 208 times the cosine of 30 degrees. So we have that one, and we could find what that is. Give it a second here. That's 3 divided by pi times root 2 times 208. So that's 281 approximately times cosine of alpha, or cosine of 30, which we know is 0.866. And so that is 243.35. So the nominal rated current we can find IF nominal rated current is the nominal field voltage divided by R sub F. So that's 243.35 divided by the field resistance I gave you, which was 1.5 ohms. And so that is 162.2 amps. Okay, so if we're going to let's look at number 1F. And what you're asked to do was to say operate at 2 times nominal rated speed. So I think that was the nominal. Let's see. The rated speed was 990, so that 2 times 990 must be 1980, right? Let's see, nominal was 990. Yep, 990 RPM. which is equal to 1980 RPM. So let's convert this to radians per second. So this would be what we call N, right? Now the mechanical speed in radians per second is going to be pi over 30 times 1980. So that is going to be pi divided by 30 times 1980 is 207.435 radians per second. Now let's use that standard equation for the equivalent circuit of the armature. VA is equal to RA times IA plus lambda AF times omega M. Now what we need to do in this case is that we're going to run. Now I didn't say otherwise, so if I don't say otherwise, assume you're operating at the nominal current that we should have found for this, right? So let's find that. Find nominal IA. So if we do that, we know that we're trying to supply 7.5 kilowatts shaft power. I'm going to end up working this whole problem here to answer your question, right? So we have P shaft that's being applied is 7.5 kilowatts. And that would, if we look at nominal, that's at 990 RPM, or omega M, nominal rated. Well, actually, it's not nominal, it's rated, right? We're just talking about a rated load, rated for the application. So the rated was going to be pi over 30 times 990. That is 103.7 radians per second. Okay. So we also gave you damping losses, right? B is equal to 0.05 Newton meters seconds. We know from this, what we've been talking about is the loss of the mechanical loss of the shaft. That is going to be B times omega M squared. Remember that? Because we know that T loss, mechanical, is B times omega M. So we have, and we know that a power, right? Power is torque times speed. So the P loss, mechanical, is going to be the T loss, mechanical, times omega M. That's why you got the squared there. Okay, so that's 0.05 times 103.7 squared. So 0.05 times 103.7 squared is 537.7 watts. Okay, so we know that the P mechanical, that's supplied from the motor, the P mechanical has to be equal to the P shaft plus P loss mechanical. We've got to supply both this is the load, right, and that's the losses. So if we Let me make a little bit of room here. The P mechanical is equal to 7,500 watts plus 537.7. That is 8,037.7 watts. Okay. Now we let's take a little shortcut because we're just trying to find IA, and it always helps to say there's more than one way to calculate something. So we're operating under rated conditions and the nominal conditions of the motor. So we know that P mechanical is going to be equal to EA, that's the nominal rated, times the armature current of the rated condition that we're operating under here. Then we're after I sub A. We know what E sub A nominal rated is. It's the lambda AF that I gave you, and it's the speed times the speed that we calculated there, times IA rated. So IA rated is going to be equal to P mechanical. So I'm solving something, probably number A or something here. It's P mechanical divided by lambda AF times the omega MR. That's going to be equal to 8,037.7. And then I gave you the lambda AF is 1.5 volt seconds times 103.7. And that is equal to, so divide the 1.5 divided by 103.7. So it should be 51.7 amps. So we're working this problem back from the load. Is everybody clear on this? Okay. We know IA rated now, right? So let's return to problem 1F. Because we know pretty much everything. First, we've got V sub A. We need to talk about this. See, I keep finding the new concept here, right? IA rated plus lambda AF. Now, this is not nominal. We're going to have to find this. But we also have to find this, because this is what's limiting us. So lambda AF times omega M, and we're under that rated condition. Now, remember what we have, and just to simplify the concept of, and we're going to talk about this, I plan to go through the actual implementation of the unipolar PWM controlled motor, just looking at it from the power electronics side. But this is my little shorthand symbol for an IGBT or a MOSFET. And then you've got some inductance there, which we ignore in the steady state. We've got the R sub A, and we have the E sub A here. We have the input voltage that's basically, if you're running off a battery, it'd be exactly that, but we know that what this really is, because you're running off of a line, right? We have a rectifier here, and it's basically being synthesized we're converting AC to DC through a full bridge rectifier, but unlike the thyristor controlled condition, we actually are feeding into a we can think of what does the motor look like from the source, okay? So this picture here is what does the source look like from the motor perspective. It doesn't care whether it's got a three-phase full bridge rectified source or a battery. It's going to look the same. From this is a voltage sink here, which is really, this whole thing looks like that to the source. And in reality, it's creating this voltage, that's V sub I. Now, because it's a stiff voltage sink, which is really, what does a voltage sink look like? Typically, it's a capacitor with some kind of a load coming out of it, right? That's exactly what the motor looks like from the perspective of the source. Because it's doing that, we can say that V sub I is equal to square root of 2 times V line to line. It's approximate. I had this in the notes I posted. You know, you can get technical about this. There's a little bit of ripple on the capacitor, but for the most part, what the capacitor does is it completely smooths out. You've got, 6 pulse rectified voltages, and it's going to basically try to run right along the top of those, and create, it's going to create V sub I from the peaks. So we know what V sub I peak is because we know now we're driving the source. It's 208. Same thing at the field, and there's no transformer to the field in this case. They're both being driven off of 208 volts. So we know that V sub I in this case, it's different from what the V sub F is. Because V sub F is a phase controlled rectifier. It's root 2 times 4 or times 208. 290, see, root 2 times 208 is 294 volts. Now that would be, assuming we have an idealized converter, that would be VA max. However, I gave you a limitation. I said that the max operating duty cycle D is 0.8. So remember, what is this? What are we doing here? What the this converter here, we're going to talk about this today, but this is a full bridge converter. It's supplying a voltage that looks like this to repetitive pulsed voltages over a period of t, where t is equal to 1 over a switching frequency, how fast you turn, the frequency at which you turn devices on and off. And then this period here is d times t. So we know that we're after the average voltage of V sub I. That's the voltage here applied to the motor. That becomes V sub A. So that is going to be 1 over the period t integral 0 to t. Actually, it's from it would be this 0. I think maybe in my notes I made this a little bit not exact. I was rushing. 0 to d to sub t, it's going to be v sub I. Yeah, my note was screwed up. Sorry. And then from dt to t, it's going to be 0 dt. If you took power electronics, you wouldn't have been confused. I was rushing and probably tired. Okay. Okay, so but what does that really end up being? It ends up being, this is 0. It ends up being dvi when you solve this whole thing. That's the armature voltage. So what I've said is that, and we talked about operating on the maximum peak max, the P max capacity set by the drive. Remember, P max is equal to the V max that the drive can supply times the I max that the motor can handle in the steady state, right? That means thermal. So this is a thermal limit. And this is, it's a combination of the source and the drive power electronics and the controls. So why I said 0.8 is because we're assuming we're operating at steady state of a drive that's actually dynamically going to control up to twice rated speed. So this gives you a margin of control. You could go all the way to 1, but you would completely lose control at d equal 1. And this will become clear as we go into the dynamic things. But see, that's basically a margin of the controls to control speed and torque. So we won't want to, run our D all the way to the end there. So, you guys with me on this? Have I lost you?
I'm here.
You guys are all is it making sense, Mike?
Yeah.
Okay, so we're back to this thing. VA is equal to 0.8 times 294 volts, right? 294 plus R sub A, which I gave you to be 0.26 ohms, times the I sub A, which we calculated to be 51.7. What am I saying here? Sorry. This is equal to this. This is R times IA plus lambda AF, which is 1.5, and times the, well, actually, we don't know lambda AF. Okay, we've got to find it. It's a question. Lambda AF times omega M, right, which we know to be, going back to the whole problem, back to the beginning here, that was 207.35. That's the speed. That's double rated speed. 207.5, is that right? Or 0.35? I can't remember. I'm getting old. Did I say 207.5 or 35? I mean, why am I having two significant digits and being idiotic here, right? It should be 207.4, really. Just let's round things up a little bit here. It never hurts to round because it always gives you margin. The only reason I might not round is, your numbers change when you're in school. You say, oh, the number's off by 0.01, I did something wrong. Well, no, it might be off, and sometimes it may, if you're on the scale of 1,000, you might be off by 1 or 2 amps, so that, or even 10 amps. That doesn't matter either, So, in the real world, you don't have to have, you're never going to have exact numbers. But we have to find lambda AF. So that's going to be VA minus RA times IA divided by the speed. So that is 0.8294 minus 0.26 times 51 divided by 207.4. And then that is going to be 0.8 times 294 minus 0.25 times 51. It's 222.45. Here I am again. It's 0.5 because, okay, 207.4 divided by 207.4. That's 1.07. Now I had a lambda AF of 1.5. So this says that I have to reduce lambda AF. Well, it's pretty simple at this point. I had to reduce it by reducing the nominal field. Since I went ahead and did this all the way to the field current, you could probably take some shortcuts, but let's just do that. We know that what we're doing is we're saying that the lambda AF is equal to lambda AF nominal rated times the ratio of the current. So the IF that we're operating at divided by the IF nominal rated. Okay, so we know that the nominal lambda AF is 1.5. We don't know I sub F. We knew that the field, the nominal rated, calculated that back up here, was 162.2. And we need to get to 1.07. So I sub F is going to be equal to 162.2 divided by 1.5 times 1.07. There's so many ways you could do this that are maybe more efficient than what we just did. Okay, so that is 115.7 amps. Okay, so what's V sub F? V sub F is going to be R sub F, which was 1.5, right? It's R sub F IF. That's going to be 1.5 times 115.7. 173.6 volts. Do you know what we need to do now to get alpha D? Is it clear?
Yeah.
I mean alpha F? Right. You know this. Find alpha F. Okay? You guys can figure the rest out, right? But I think it's maybe a good review of what we just learned. That's why I took the time. Is there any other questions on this? Okay. So we're going to talk about a 4-quadrant operation of the motor drive. And I got a chance here to make a correction. I got to find the little pen colors here. Whoops, turn. To something that I said in class. See, this is why I don't like to use this, because I can't draw a straight line to save my life. Okay, that's omega m, and that's omega e. And remember that last time in class we talked about, let me, I pointed out that everything we had done up until we talked about reversing the direction of the speed was operating what we call the first quadrant. So that quadrant would be where the mechanical speed is positive and the torque is positive. So that's quadrant 1. Well, I said, what about if we reversed the speed and we're going to operate? We actually are also trying to operate as a motor. So if we reverse the speed and we're operating as a motor, what we're really trying to do is we're trying, and it can be confusing sometimes here. What we're doing here is we're saying I'm trying to apply P mechanical that's greater than 0. That's, I'm motoring. I'm operating as a motor. Well, I go in the opposite direction. I still want to motor, so I still want P mechanical to be greater than 0. So even though the speed went negative, so I'm at a negative speed now, I also have to make my torque negative so that the product of those is positive. So that actually puts me in quadrant 3. And I think I made the mistake of just being late, not thinking, saying that we were in quadrant 2. We were in quadrant 3 at the end of the class. Is that clear to everybody? Does anybody not understand that? Somebody say yes or no. Okay. Should be completely clear. We didn't talk about these other modes of operation. So it's possible that, and we're going to get into this in great detail when we go to the next module. It's possible to operate at positive speed but negative torque. Now what you're doing is you're regenerating back. So you have to have a drive that can handle that. The drive that we've talked about so far cannot do that because they have a diode bridge front end. The diode bridges are going to block the reverse power flow. But it is possible to operate in 4 quadrants. So what we want to do is we want to be able to have a a converter that can operate in all quadrants. See, I can't see. This is the worst thing about PowerPoint. In presentation mode, I can't advance my screen. I want to operate in all quadrants. Now, if you look at it from the power converter side, you can say, yeah, I got to operate in 4 quadrants. Let's say my converter's producing an output voltage and an output current. I'm in quadrant 1. I'm in quadrant 3, but I also would want to be able in quadrant 2 and 4. So it goes 1, 2, 3, 4. So the 4 quadrant chopper is really the power electronic converter that's going to enable us to do that. This is a different representation of it. But basically this is a switching device and the diode and in parallel. So that's effectively, if we look at this so far, it's just a slightly different picture. We're looking at it as that thing right there. That's an IGBT because I've got a completely control. I've got the basically voltage blocking unidirectional switch here. And then I've got this diode which cancels out my voltage blocking capability because if the voltage gets, if this voltage, the V diode in that direction, or we call that the V from anode to cathode, is greater than, say, 0.5 volts or something, this thyristor's going to, this diode's going to start conducting. If it was a thyristor, you could hold off conduction, until you turn on your gate. But this is not what we got. We've got this diode. But basically, the point is I've got this switch, which I can use, and I have that shorthand symbol for it. This could also be a MOSFET. So it's all three things. So basically, you've got 4 of these switches. And I like to think about it as you got 2 leg switches, and we've labeled this. This is we're going to give this an A designation, and this B. So we could call this leg A. We could call this leg B. It's also going to be helpful if we think about the states of the switch. So I'm going to introduce that concept. I've got the SA state, and this is the switch leg state in the SB. So what basically this means is if SA equals 1, then TA, notice this is TA plus, that's the upper device, is on, and TA negative, that's the lower device, is off. Or if you say, the other way you could say is if SA is equal to 0, then TA plus is off and TA minus is on. We know we could never have these 2 devices on at the same time, or we'd be short-circuiting, because what's upstream here is a cap, right, and a voltage source. We have this is a voltage source converter, or VSC. Okay. Now this converter can operate in all 4 quadrants, because what it can do is it can operate with current flowing in this direction and a positive voltage, right? It could also operate with current coming the other direction with a positive voltage. You could also reverse the voltage and go this way and have current go both directions. So that's what this thing can do for us. This is really the core converter power electronics for any DC drive. Does it make sense? Or any questions on that? Okay, what I'm going to do now, I've got these notes here, the PowerPoint. You can go through this. This is a little bit more rigorous, but we're going to talk about unipolar switching. I'm going to explain this in a different way, a simpler way. So just bear with me a second. I've got to figure out how to get out of this mode. Jeez. They have it in presentation mode, and all the commands like practically invisible on the bottom of the thing here. Okay. All right. So let's go through this. we've got a DC source. We've got this capacitor in parallel. You might have some impedance to the source here. This is kind of like just an ideal DC source. Could also be a battery, but batteries aren't ideal, as we know. Okay, so I've got these devices. What I want to do is I want to apply a gate voltage to the four devices. Now, I'm not going to get hung up on the gate drive and all of the analog circuitry. We're just going to say if I can apply a 1, it turns on, right? So there's a 1 or a 0 or a 1 or a 0 here. 1 turns on, 0 turns off. You could also do 1 minus 1 if you want. That's how the Plex PWM controls work. But really, you're using a signal logic level, and if you're simulating, which we went over before, how are you synthesizing these things? So what you're really synthesizing is pulse trains. So we say, first of all, I've got logical states. We're trying to apply a voltage here. That's the V sub D. This is VI. And we have a and we've got a B. And so we're going to have a logical states of SA or an SB, right? And they're going to be a 1 or a 0. That's the state of the leg. But then you've got the state that's being applied to the devices. Now I'll change this. Well, this is what we call TA plus. This was transistor A minus, transistor A plus, or transistor B plus, transistor B minus. This pulse train that you're applying, that you're going to synthesize with your PW pulse width modulation controls. We'll call this one H sub A, H sub B. Sorry, it's not that. H sub A plus, H sub A minus, H sub A B plus, H sub B minus. Now we also know that H sub A minus is the complement of H sub A plus, right? And H sub B minus is the complement of A. Is that the right terminology? Complement? If H sub A minus is a 1, then H sub A plus is a 0. Did I get that right?
I don't know if that's the right term, but
What is the term? Somebody who's taken digital electronics in the last 2 years. I took it like 40 years ago. So what is it called?
that's correct. I think that's correct.
Okay. So you got it's really, the thing is, if you had an H sub A plus signal, you'd be putting it through a, doggone it, what is that thing called? Not. Sorry, just I'm getting old. A knot. You're going to knot it, right? That's the knot of, or it's really the knot. Yeah. Okay. So we remember that. So in a way, what you can do is you can characterize everything going on just with the top guys, which is typically what we do. And often, if you were going to look at S sub A as a pulse train and S sub B as a pulse train, as pulse trains. I usually think of them as just a logical state, but as pulse trains, I don't like to think of S sub A as a pulse train, but S sub A is equal to HA plus. S sub B is equal to HB plus. But as you look in literature or online, things like that, they'll often interchange these things. Okay, so what we're really trying to do is we want to create pulse trains that are going to give us, our goal here, at least for, let's just say, quadrant 2, or quadrant 1, is that we want V sub D, which is what the average of that is going to be equal to some duty cycle times V sub I, right? So to do that, the simplest way to think about this is we're doing everything, at the logic level, which is between 1 and negative 1. And what I'm going to do is have a triangle. So we're going to say this is V triangle. And it's going to, see, guess it's fine wherever we end up is fine. Starts at 0, goes down to 0, but then it's going to go down. So this is 1, and this is minus 1. Now the PowerPoint notes make these arbitrary numbers, so you could make those a voltage, so it could be like an analog circuit or something. But more if I'm nowadays, you can create these things with an FPGA. So I'm thinking more in that line, just ones and zeros, it's all logic. And okay, so you got V triangle. Now what we're going to do is going to come up with a controlled voltage and this is, I'm going to call this D sub A, that duty cycle applied to the phase A leg. We can also put, there's going to be a duty cycle applied to the phase B leg, D sub B. It's going to look like this. So what this really tells me is that, say, D sub A or D sub B is equal to the negative of D sub A. And I'm going to compare these two together. So what that means is I'm going to have a duty cycle that gets D sub A, say for example. This is actually coming from controls. This is why you do not want to use pulse generators. Okay, that's a big no-no, and nobody should ever teach you to do that in power electronics. If they did, they really did you a disservice. Okay, this is the triangle here. So you have this is just a simple logic thing. It's exactly how it would look in Simulink. And if dA is greater than, or let's say it's the other way around, if no, okay, let me think for a moment. If dA is greater than V triangle, That's what this is. Then what you're going to get is a 1. Otherwise, you're going to get a 0. So let's create, we're actually going to be able to synthesize S sub A right here and S sub B for that matter. So here's, or not S sub A, I'm not going to fall into that trap. I'm going to call this H sub A. I'm just being a bit of a purist, okay? H sub A plus, just because I'm being consistent in what I call stuff. And this would be H sub B plus. Some people might call this S sub A. Probably they do it in the textbook. S sub B, if they even do it in Christian. I don't even know. Okay, so what I'm saying is let's just find the points of intersection right here. So if D sub A is greater than this triangle, then that means that I have a 1. But then the triangle goes above it. I now have a 0. So we'll go to the next intersection point right here. It's going to go back down below it. It's going to stay there up until this point right here. I'm just looking at the comparison between D sub A and the triangle. You can see that I've come up with a really nice pattern here that I can get my duty cycle out of. So one thing to make clear too, let's establish the period. So I start the triangle at this point, and then it starts to repeat. So this repetitive triangle. So that's what we call the period. Remember, the period was 1 over the switching frequency of the devices, because the devices, this is going to cause a device to change state every time one of these crossing points occurs. Does it make sense? So now let's talk about the synthesis of H sub B plus. So I've redrawn this part here, and we've got coming out of this is H sub A plus, and then we'll have coming out of the bottom H sub B plus. The gate signals to the top devices in the two phases. And again, same thing, if D sub A is greater than V triangle, we should have a 1. Otherwise, we'll have a 0. So looking again at what's going on here at the beginning, V triangle is higher than D sub B, which is down here. It's a negative. So that would mean that we would have a 0 coming out of H sub B all the way up until we get to the cross point right here. And then at that point, D sub B is higher than the triangle. So we have a pulse, but then it goes below the triangle goes above it for the rest of the time. So that's the H sub B pulse. Now we've got some interesting thing going on here. We know that this period, this time here, is the period. Just looking in on one of these periods. So the pulse width itself will end up being D times T. Just naturally, that's what we've got. And that's for the phase A leg, but the phase B leg, interestingly, is going to be 1 minus d times t. So what we really want to understand is how do we get the synthesis of the voltage between points A and point B. To do that, let's take this waveform here. It's not as clean as I'd like it, but you get the idea. We can look at this a fairly simple way, and we could say that what we're really interested in is some synthesized pulse of HAB. And we can get that simply by subtracting these from each other, HA minus HB. So let's see what that would give us down here. We'll call that HAB. And so we have HA minus 0, we have a 1, then we have a 0, we've got HA minus 0 again, up until this point, and then HA minus HB is a 0 here. Then it's HA plus minus B is 0 is 1. And it would continue there until we get to the final point here of what we represented. It goes back up. So we actually have multiple pulses occurring here. Looking at this center portion that we looked at before, the period, we actually have 2 repeating pulses happening in that period now of t over 2. And it will actually turn out, you could see this better if I used graphing or something, but that this is the proportional time to t of d over 2. So this is dt over 2, d times t over 2. If we want to know what the voltage that we're going to synthesize would be, the HAB represents, say for example, if HA plus, this time here, is 1, HB plus is 0, that means that device is on. So I'm going to give this a little letter or a little number to help us. We'll just call this is during the period 1. Well, let's start over again. We'll start at the beginning of the period right here. So we can pick our periods anywhere. We're just going to say we're going to analyze at least part of this period. We may not have to go any further than this to figure out what's going on. So we'll call this state 1, and we could call this state 2 for lack of a better name. And going back up then during state 1, let's say state 1, I'm going to give it this color of yellow. Okay, and then during state 2 we'll color the path with, say, orange. Okay, so during state 1, TA1 is, this is HA1 is 1, so TA1 is going to be on. That would mean that TA minus is off. On the phase B, since we have a 0, TB plus is off, but TB minus is on. So we're going to apply the voltage VI across from A to B. The amplitude VI. And then during the 2 time, we actually have A plus and B plus are both on. So going back up to our picture here, that's during the 2. A is on, but now we've turned B on. If B is on, TB plus is on, TB minus must be off. So then a 0 volts gets applied from A to B. Which is what I started to draw here. Now we're going to go back and we look at what's happening. We're going to go back exactly to this state here. So we're going back exactly to the 1 state here during this time. And that means that we'll apply VI again. And then we're going to go to a 0 state, but in this case we're at a 0 state because HA is off and HB is off. So this is a 3rd state. That creates 0 voltage. And this pattern is going to repeat every period. So if we look at what's happening there, let's add a 3rd period, and I'll give it a different color. During that, no, green's a bad color. Let's pick this color here, blue. So now TA plus is 0, that means TA1 is on, and TB plus is 0, which means TB minus is on. So we have both of these, but we're applying a 0 except by switching these two. So you have a very interesting thing that happens. This is what's called adjacent state switching. At the beginning of the period, you are going to start with a state. If we use this 1, 0 for SA and SB, we can pick 1 or minus 1 or 1 or 0. It depends on how we're going to use these logic levels. So I'm going to kind of point that out here. We're going to use a 1 if either these on, a 0 if it's off. So essentially, the first state, state 1, has a 1. It's 1, 0. State 2 is a 1, 1. State 3 is a, well, we're actually going to go from 1 to 2, back to 1 again, and then we're going to go to 3, which is a 0, 0. Now, what we're doing is we're actually following a sequence here. So we go in sequence 1, we're going to go 1, 0 state. So this is the state of 1 switch. This is another state. This is the commutation state of the other leg. We're going to change one switch state per leg in every sequence. So in number 2, we change the state of the B, but we leave A where it is. So that will give us a 1, 1. This produces VI. This produces a 0. Then we're going to go to 3. And in 3, we're going to go back to state 1 again. Sorry. The next sequence is we're going to go to 1 again, which gives us a 1, 0. So we haven't changed the A state at all. We've changed the B state twice. We had turned the upper device was off. We turned the upper device on. Now we're going to turn the upper device off again. And then in the third state, we're going to go to a 0, 0, which means we're not going to change the state of the B switches. Not going to change the state of the B switches. We're going to change the state of the A switches. We're going to turn the upper A device off and the lower one on. So what this means is that to create 4 pulses per period, we've only switched each device one time per period. So that's called adjacent state switching. We've also balancing out the losses between all these devices by balancing the we're also balancing out the losses in every device. That's what you do when you achieve adjacent state switching. So what's happening is, because we're switching this way, we're going to give this a name, this type of pulse width modulation approach. It's called unipolar PWM. And it is actually going to give us a 2 times switching frequency pulse rate on the VD that's applied to the drive. Oh, crap. And we're only going to switch each device one time per period. And we're going to equal out the losses. So this is a very beneficial way to apply a 4-quadrant full bridge converter to a DC to DC converter. It's going to do two things. It's going to give us a low current ripple, because essentially there will be a corresponding, I don't know why this is doing this, armature current when you're in this state 1. The armature current will rise. It's building up energy because you're applying a voltage to the armature. And then in this, you're freewheeling, you're applying zero, so the armature current will go down. It's going to rise again and go down. And so you get two pulses basically in your ripple current per period.